Hello, ladies and gentlemen. I'm here to go ahead and go over a few things for section 17.3 on rate laws. So I'm going to do something a little different this time. I'm going to go ahead and I'm going to um, change things up a little bit and actually kind of go over a sample problem and the ideas at the same time. So there's no separate PowerPoint. I'm just kind of talk about the ideas that are going on here. Okay. So in section 17.3, they talk about rate laws, and what rate laws are equations. And so right now, what I have here is I have an example of a rate law right here. This is what a rate law would look like, and let me explain what it will do. So it's pointing that out here. I'm going to erase it just so that pointing it out because I don't know if this is coming out sometimes. So this represents an equation that represents how fast the chemical reaction at the top here is going. So here I have this chemical reaction, H2 plus I2 going to form 2HI. And one of the things that we said earlier was or at least in the earlier part of the chapter, we talked about was that rate is related to concentrations. So a rate law would have a place here where you can go ahead and plug in the concentrations. So see these little brackets right here? And I think I've mentioned it in passing, but really haven't gone into a lot of detail. So these little brackets right here represent the concentration. So when you put a formula inside here, um, it's um, it represents concentration. So H2 in brackets right here represents the concentration of H2. I2 in brackets represents the concentration of I2. And so in order to use a rate law, and I don't think they do, most books don't do a really good job of explaining this, so that's why I'm going over this. You go ahead and plug in your concentration of H2 at any point in time, and your concentration of I2 at any point in time. And then at some other point in time, if these are reactants, so they'll generally tend to decrease over time. But you can even use this, at another point in time when you've replenished some H2 or I2. You plug those in, and then you multiply the numbers together along with this thing, which is called a rate constant. And when you multiply the two things together, or all the numbers together, you get a rate. Okay, and we can do a little sample of one right now in just a little bit. But right now I'm just kind of doing this just to kind of show you kind of how that would all work. So you plug those numbers in. So a general rate law takes this general form right here. And so go ahead and change the color. It takes this form. And as you can see, our rate law up here is going to be that form. It always starts with R equals, and R is the rate of the overall reaction. Remember we talked about in an earlier PowerPoint how R could be the rate of one reactant or the other, or vice versa. In general, normally we assume that this is the rate of the overall reaction, which remember is also equal to the rate of any substance with a coefficient of 1. Anything with a coefficient of 2 goes twice as fast. Anything with a coefficient of 3 goes 3 times as fast, etc. and so on. Okay. So it's always R equals to some K. That's your rate constant, and it's a lowercase k. Next chapter, we're going to be using capital K. So make sure you make it lowercase so you know what you're talking about. We know what you're talking about. And in this case, the K here, it's a value. And it'll have units that once you multiply it by the concentrations, should leave you with something like moles per liter per second, or grams per second, or whatever units might be. Your rates, remember we said, was an amount or quantity over time. So the rate should end up with those types of units. Concentrations are usually in moles per liter. So the units of rate really depend on the rate constant here, really depend on what the concentrations are, what the rate law is, and what the order of the rate law the rate law is. Order of the rate law is the exponent here. Okay. The orders generally tend to be, although there are a few exceptions, they tend to be whole number integers. So here we would say that this is first order with respect to hydrogen. So hydrogen is first order. Why? Because the exponent in the rate law is 1. And for iodine, we say it's second order. Because the exponent is 2. And there are definitely implications for the rates and the rate law when it comes to what order it is. Okay? Those with higher orders tend to have a bigger effect on rates, especially when you change the concentration. Those with lower orders tend to not. And you can even have a 0 order. And when something is 0 order, it means it has no effect on the rate. So you can double, triple, put in 10 times as much, it's not going to change the rate. It doesn't mean it's going to stop the reaction. It means it's not going to change the rate. So you have a rate constant. So it's R is equal to some constant times the concentration of reactant 1 to some power, right? We should call it the order with respect to that reactant, times the concentration of the second reactant raised to some other power to its order, the order with respect to that reactant. All rate laws, and we call this the differential rate law. In this class, that's all we're going to use. So I'll just call them rate laws. All rate laws take this format. So R is equal to K. You can always write R is equal to K. They will always start that way. Then you just multiply by the concentration of reactant 1 to the X power times concentration of reactant 2 to the Y power. So the difference between this one and this one, as you can see, is that the first one here, let me go ahead and erase a lot of this stuff so we can go ahead and go back and work from scratch. Don't want to, that's why I didn't just swipe them all off. I didn't want to get rid of my equations. So here is my K. And here is my X. And here is my Y. Okay. So what we're going to be doing here is we're going to actually be looking for what those are, what the form of the rate law is. We have the general form, but in order to have a rate law that works, you need to have the orders, right, the exponents, and you need to have the equilibrium constant. Okay. So let me just go ahead, before I go ahead and do a problem that shows how we can get that, how we can get this whole thing right here. Let me go ahead and show you how it would be put to use. One thing I find that books don't do is they never tell you, you know, well, what good is this rate law? They tell you how to get a rate law, but they don't tell you what the rate law is. So let's take this equation right here. Let's say we have this chemical reaction, and we want to know how fast the rate is going at a certain point in time. And at a certain point in time means, you know, at certain concentrations. So let's say at a certain point in time, the concentration is H2 is equal to 0.05 molar. And the concentration of I2 is 0.2 molar equals 0.0 molar. Okay, so those are, at any point in time, we measured the concentration of H2 is this, concentration of I2 is that. All you do is take the equation and plug it in. We got R equals to K, which is, in this case, we already know what our K is, 3.42 times 10 to the negative third molar to the negative 2 times second to the negative 1 times H2. Now, instead of putting brackets, once I put numbers in, I tend to put parentheses. Why? Because everybody else does it. 0.05, and it's to the first. And the second one is I2 concentration is 0.2. And that one is squared. All right, so if I go ahead and plug these numbers in here, I'm going to get my calculator to go ahead and do that. What I'm going to do is I'm going to start off by going 0.2 squared. It's going to give me 0.04 times 0.05 times 3.42 times 10 to the minus 3. And when I do that, I get 6.84 times 10 to the negative 3, 4, 5, 6. 10 to the negative 6. Okay. So 6.84. 6.84 times 10 to the negative 6. And oops, I forgot to put the units in here. Put the units in here. Molarity and molarity, sorry. What I'm going to end up with is molar here times molar squared here. So I got molar cubed times molar to the negative 2. So there's a positive 3 and a minus 2. And remember that molar to the negative 2 means 1 over molar to the second. Really, my units are going to be something like molar cubed because of these guys right here, because of concentrations, and molar to the second in the denominator. That's from this right here. And so basically I'm going to end up with molar per second, because second to the negative 1 is the same as per second. Okay. So there I would have the rate of my reaction. What this is telling me is that the rate of the reaction at this point is 6.84 times 10 to the negative 6 moles per liter every second. So every second, I'm losing 6.84 times 10 to the negative 6 moles per liter of hydrogen, and 6.84 times 10 to the negative 6 moles per liter of iodine. I can use for either one. Why? Because they're both have coefficients of 1. So they're equal to the overall rate of the reaction. In this case, go ahead and so that's what I would use. Now, we said earlier that concentrations vary based on, well, rates can vary based on concentrations. Right? If you change the concentration, you can change the rate. So let's see what if we just change the concentration. Let's make the concentration here, H2, let's make it 1.0 molar. And I2, let's make the concentration I2 1.5 molar. So as you can see, they're substantially higher concentrations. Actually, H2 is like 20 times more concentrated, and I2 is 7.5 times more concentrated. So higher concentration. So if you plug these numbers in, let's see what happens to our rate. R is equal to, the rate constant is just that, it's constant, always the same. Just put it in 3.42 times 10 minus 3 molar to the negative 2 times second to the negative 1. There's my K. Times the concentration of H2, which is 1.0 molar. That's the first. And concentration of I2. Is actually a number, 1.5 molar. Now I'm going to square that one. Once again, the reason I square this one and the H2 concentration doesn't get squared is because my rate law tells me up here. I'm just doing what the rate law says. And if I plug these numbers into the calculator, once again, so I have to square the concentration of I2. Well, I'm going to plug that in first. 1.5 squared is equal to 2.25 times the concentration of H2, which is 1, times 3.42 times 10 to the minus 3. And what I get here is 7.70 times 10 to the minus 3. So 7.70 times 10 to the minus 3. And my units, again, are molar per second. Once again, the units come from molar, the second power is molar squared times another molar, molar to the third, multiplied by molar to the negative second. Really just add exponents. Negative 2 plus 3 is a positive 1. You will notice then that colors here. My rate is much larger now. It's 10 to the negative 3 versus 10 to the negative 6. That's like 1,000 times faster. That's because we plugged in concentration. So here, this shows you that concentration does have an effect. Just like in the last section, you saw that one of the things that affects reaction rates is concentration. And here, we changed the concentration. Same rate law, we changed the concentration. It went from 0.05 and 0.2 to 1 and 1.5. We increased both of them, and by increasing both of them, we went ahead and increased the overall rate. Okay. One last point before I go on to our sample problem. This is not the sample problem. This is just kind of to show you how you can use a rate law. What a rate law would actually look like, and what where it comes from. But just to point one other thing out here is that another factor that changes rates is your temperature, right? As the temperature increases, the rate picks up. Temperature decreases, the rate picks up. Well, where in this rate law is temperature come in? Comes in here. If the temperature increases, so this is the rate constant at this particular temperature. If the temperature increases, then your rate, you have to find another rate constant. The rate constant is going to change. Your K here is going to change. So this is what affects, or this is affected by the temperature. Okay. So concentrations go here, temperature goes here, and there are other things that you learned about, and sometimes they come into play, but for the most part, in all reactants, the rate law has the concentration component in it and also the temperature component. Okay, so let's go ahead and see what a sample problem would look like for you to do. This was just an introduction on what a rate law looks like, where it comes from, and how you would use it. So I think some things that some books don't show, but I wanted to show before I did the rate law problem, because if you learn how to come up with a rate law, but you're like, well, what will I ever use that for? And you're like, well, why am I even doing this? But and we can plug numbers in, and we can actually get rates. Okay, so let's go ahead and try a problem like you would get in a homework assignment. And I have that problem up here. Go in here. Up here in the screen here. This problem says, determine the rate law for the following reaction given the accompanying empirical data. So a rate law is determined what we call empirically. In other words, it's determined through experimentation. You got to do an experiment to figure out what is going to be the order with respect to each reactant. As we mentioned earlier, the order is the exponent for the concentration of each reactant. We can start off by color here. Looking at this chemical equation, I can write that the rate law is going to take this form. R equals to K, always R equals to K, and that should be lowercase k. Lowercase k, in case you're wondering. And then I got two reactants in this equation. I have NO. So K times the concentration of NO. Put the NO in brackets. And it's going to be to some power, X, times the concentration of the second reactant, which is chlorine or Cl2. That brackets. And then it's going to be to some power. So this is going to be the general form of this reaction. R, your rate, is going to be equal to some K times the concentration of NO to the X times the concentration of Cl2 to the Y. Okay. That's the general form it takes. They always take this form. They always start with R is equal to K. And then the only difference from one reaction to the other is what the identity of the reactants are. One's to the X, another one's to the Y. Generally, most chemical reactions have one or two reactants, so usually don't go more than that. But there are a few exceptions that go to third. I don't think I've ever seen one to fourth, because that's a whole bunch of things colliding with each other. That's not going to work. Okay, so what happened is this. You got some data right here, and this data has concentration of NO. Notice right after the concentration of NO, there's a 0. That's an initial rate, because when a chemical reaction starts, we can measure the initial rate. Then it changes, but it's kind of hard to do that. So what we do is we do it right at that point in time. It actually turns out that as the concentration changes, so does the rate, because if this number changes, then so does the rate. So we're just going to pick the initial rate of NO, column for the initial rates of chlorine, Cl2, and then a column for the actual rate. These have been measured. So you set the concentrations, and then you measure the rates. And then what you're going to do is use those numbers in order to figure out what the X and the Y are. And once we've calculated the X and the Y, then we can go ahead and calculate the K. Okay, so that's going to be our strategy. And then that'll give us our rate law. I might have to scroll down on this a few times to be able to get all this stuff. So basically what you can do is take an idea of good science. And in good science, what you do is test two things and how one thing changes while the second thing changes. And so how correlated they are. And one thing you're going to notice on this information you have here is that two of the experiments, so we'll call this one experiment 1, experiment 2, and experiment 3. So the same thing is happening, but we've varied the concentrations for each time we did it. So we'll call this one experiment 1, experiment 2, and experiment 3. Experiment 1 and 2 have the same concentration of NO. So we're going to keep the concentration of NO the same. We're going to vary the concentration of Cl2. And we're going to measure the rate and see how that varies. This way, we know that however that rate of varies between the two, that's all because of the concentration of Cl2. That'll tell us to what degree chlorine is. So what we're going to do is we're going to go ahead and take the information from each of these, two of these experiments, and plug them into the equation here. And really what I'm going to do is I'm going to go ahead and go, and I'll write this down here, is experiment 2 information. So experiment 2 all over experiment 1. If all these weeks of practice, my writing would get better on this one now. So that's experiment 2 of experiment 1. Sorry if that looks hieroglyphic or whatever. So in experiment 2, we have the rate. If we look at the rate over here, it's 0.50. I'm not going to put the units in because it creates more of a mess, and they're all going to cancel anyway. So I'm going to put basically all the information for experiment 2 on top. So R is 0.50 equals to K. And all these should have the same K, so I'm just going to put K right here. Times the concentration of NO, and NO is 0.10 in experiment 2, the X. And the concentration of Cl2, and in this case it's 0.20 to the Y. So all I did was I took the information from the second the second experiment and just plugged it into the format here for the equation. At least all the information I had. I had the rate, I had the concentration of NO, and concentration of Cl2. The K I leave, the X and the Y I leave. Then I do the same thing for experiment 1. So I'm going to divide by the rate of experiment 1. So experiment 1 is right here. And the rate of experiment 1 is 0.025. 0.025. Oops, I'm sorry. I'm actually put the wrong number down here. I'm gonna fix that. Because it's not 0.5, it's 0.05. Oh. All right, so this is the rate for experiment 2, this is the rate for experiment 1. That's going to equal to the K for experiment 1 is the same. They're always the same. The concentration of NO for experiment 1 is 0.10 to the X. Concentration for experiment 2 of Cl2 is 0.1. I'm sorry, experiment 1 to the Y. So these are the numbers I had in experiment 1. 0.025, 0.1, and 0.1. 0.025, 0.1. Okay. So hopefully you can see that all these numbers came just by taking the information from experiment 2 and plugging it into the format here that I had, and then dividing it by all the information from experiment 1, we're also plugging into the format for the rate law. Now you will notice that a few things cancel out. K's cancel. The same K, so they're going to cancel. And since we set the concentration of NO to be 0.1 on both, then it cancels. Doesn't matter what X is. If it's 0.1 to the X over 0.1 to the X, that's going to be 1. So now what I'm going to do is I'm going to go ahead and take this over this, 0.05 divided by 0.025. If I plug that into my calculator, I get 2.0 equals 2. And here, 0.2 to the Y divided by 0.1 to the Y. That's the same thing as writing 0.20 over 0.10 all to the Y. Right? So 0.2 over 0.1 is 2. So it's going to be 2. So if I have 2 to the Y equals 2, what does Y have to be? Y has to equal. Okay. So now I know that my Y is going to be 1. All right, that's step 1 of 3. Don't worry, it's not all going to take this long. It's just the first time it's going to explain it. So I'm going to have to move this stuff down. Let me go ahead and move this down here also, so we can do the next part. So now we know that your Y is 1. Let's try to figure out X. What I'm going to do in order to figure out X is take another couple of reactions, experiments, I should say, that have the same concentration of, in this case, chlorine. Those are 1, 2, and 3. And you will notice that experiments 2 and 3 have the same concentration of chlorine. So just like experiments 1 and 2 had the same concentration of NO, and it allowed for the concentrations of NO to cancel out so we can solve for the exponent of chlorine, now we're going to do the same thing with chlorine. So what we're going to do is we're going to use experiment 3. And the reason I'm going to experiment 3 over experiment 2 is I've also noticed that the numbers are bigger on experiment 3 than experiment 2. Just like I noticed the numbers were bigger for experiment 2 over experiment 1. You could do it the other way around, but then you're going to end up with fractions and decimals. So I tend to like to put the bigger numbers on top. So once again, the format is R is equal to K times the concentration of NO to the X. Concentration of Cl2 to the Y. In this case, we already found that the Y is 1. Whether we put that in there or not, it's not going to matter because you're going to see that the concentrations of chlorine are going to cancel out. So I'm not gonna worry about it. I'll just put it to the Y. Yeah. Either way, it'll work. All right, so let's plug in the numbers for experiment 3 over experiment 2 in this format. R for experiment 3 is 0.250. That's our rate. Is going to be equal to K times the concentration of NO. And here for experiment 3, concentration of NO is 0.50 to the X times the concentration of Cl2, which is 0.20 to the Y. All right, so that's experiment 3. Here's your rate, 0.250. K is just K. Concentration of NO is 0.50 to the X. Concentration of Cl2 is 0.2 to the Y. For experiment 2, same data, just for a different experiment. Rate is 0.050. is equal to K times the concentration of, and O is 0.10 to the X. And for Cl2, for experiment 2, is 0.20 to the Y. Okay. Once again, you'll notice the K's are both the same, so they cancel. The 0.2 to the Y over 0.2 to the Y, both of those cancel. Right, so whether I put it to the first or to the Y, it really doesn't make a difference. So now all I have is these guys, 0.25 over 0.05. If I do that, I end up with 5.0 if I plug in the calculator, and 0.5 to the X over 0.1 to the X. Once again, when they have the same exponents, it's like you can go ahead and put the bases together. 0.50 over 0.10 to the X. It's going to give you 0.5 over 0.1 is 5. 5 to the Y. And just like last time, it was 2 to the Y was 2. This time, 5 to the Y is 5, which makes, don't want to confuse that because we're using X here. So 5 to the X equals 5 means that you have X equals to 1. So in this case, both of them were 1. Sometimes they'll be 2. Like if they were 2, it'd say 5 to the X equals to 25. Or 2 to the X is equal to 4. And you'll figure it out. These all should be whole number, and they should be, all that large exponents. So they're things that you should be able to figure out. You won't need any logarithmic functions in order to do that, because you won't have exponents that are decimals or fractions, although there can be halves, even thirds. We're not going to see too much of that. That's for like college level stuff. Okay. But what we've established at this point here is that our rate, at least at this point, looks like R equals to K times concentration NO. Whoops. What happened to that? Of NO to the first. I won't write it. That's the concentration of Cl2 also to the first. So we know that this is first order with respect to NO. This is also first order with respect to Cl2. And the reaction order is just the sum of the exponents. So 1 plus 1 is equal to 2. So this reaction has an overall order of 2, which basically tells you that there are two things that affect the rate. Two substances whose concentration affects the rate. NO and the Cl2. All right, so we found those things. Last thing we need to find is, how are we going to find the K? And at this point, the K is pretty easy because you have the information, you have rates, NOs, and Cl2s. And so we can go ahead and just use our information from the these equations here. And I'm going to go ahead and move this down again. A bit more. This. There we go. Doing it here. So we have our general form of the rate law there. And so all you do is just plug stuff in. So once again, let me rewrite this so that we got R is equal to K times the concentration of NO to the first power times the concentration of Cl2 to the first power. That's big. Knowing the exponents is big. Now we can just plug it in. All right. So let's use, I don't know, let's use a second. It doesn't matter. You should get the same answer anyway because these come from the same equation. If you plug these numbers here, the concentration of NO from the second equation, concentration of Cl2 from the second equation, and the rate from the second equation, plug those into the equation. K should be the only unknown, and that will allow you to calculate what your K is. So R is 0.050, and the units are moles per liter per second. What molar times second to the negative first means is equal to K times the concentration of NO, which is 0.10 molar to the first, times the concentration of Cl2, which is 0.20 molar to the first. You didn't have the exponents, you couldn't do this. Now you can. So now we know what the exponents are. We want to solve for k. So let's do this. Divide both sides by 0.10 molar and 0.20 molar. Could have multiplied them first and do it that way. And so since we did it to this side so they cancel out, we also have to do them to the left. 0.0. By the numbers. 0.20 molar. So now your K is going to be equal to, let's get the calculator out. The calculator says, all here, take 0.05 divided by 0.1, divided again by 0.2, and what I'm going to get is 2.5. All right, in this case, the equilibrium constant at this temperature is 2.50, and the units, you'll notice that the molar here cancels with one of the molars down here, leaving you with a molar on the bottom. So you're going to end up with, really this one's on the bottom, so is this one. So you can end up with molar to the negative first and second to the negative. Okay, and there's your K, 2.50. Now you can plug that in, and you can go ahead and solve it use it like we did in the first part of the thing. So the whole rate law is R equals to, you want to plug in your K, 2.50 molar negative first times negative first. That's your K. K times and concentration of NO times the concentration of Cl2. And there it is. A little cloud. Okay. So that's the rate law, including the equilibrium constant. Sometimes people don't like doing the whole thing this way. They just kind of leave it like this. And then they tell you what the K is so you can plug it in because it looks less messy. But either way, you need a K in order to be able to calculate this thing. And you need to know the orders. And that's what we just did. Okay. So real quickly, just to summarize all this. We have this information. We use the information from the first part. We solved for y, which was the exponent of Cl2. All right, we solved for y using experiment 2 information over experiment 1 information. And once we solved for y, we knew what y was, we can solve for x. Although we could have done x first, just to let you know. And we use experiment 3 information over experiment 2 information and just plug them in. And then that gave us our rate law. In general, then all we had to do is solve for K. And we just took the information. And I'm not going to do it because I think this has gone long enough. But if you want, you can double check. If I plugged in the information from the second equation and I got the K. If you plugged in the information from the first equation or the third equation, you should get the same K. They should work out the same way. And you want to go ahead and do it just to make sure you feel comfortable doing that's the case, you can. But you plugged in all those numbers, solve for the K. Now I had a K, I can write the equation with the K in it, or I can write the equation without the K in it, but at least now I know my K so that I know when to use it, okay? So hopefully this will be helpful when you do the problems for this section. It is coming up with rate laws like this. All right, thank you for listening and hope that you found it useful and helpful.